This lecture is brought to you by CNCB Academy of Science and Technology, Orissa, India. Visit our website to know more about us. So, the title of the lecture is Aharonov Bohm Effect, the magnetic effect on fringes. So, this lecture is on Aharonov Bohm Effect or AB effect, and we will be dealing with the effect from the point of view of magnetic field only. I am Devashish Sanyal and I am an associate professor in the Department of Physics at CNCB Academy of Science and Technology. So, Aharonov Bohm effect is considered one of the wonders of quantum mechanics. It was experimentally observed in 1949, and the theoretical explanation came in 1959. Although when the theory came out, the theorists Aharonov and Bohm, they did not know about the experiment. And so what is it we are going to study here? So what is the picture? The picture is something like this. So what we have here is a bunch of electrons incident from the left hand side. So we are considering one electron that is coming from the left hand side, and here what you have, this part, this is the part where we have magnetic field, but outside this part there is no magnetic field. So what I mean to say is that this part has magnetic field, and outside this part there is no magnetic field, and the arrangement is such that the electrons which are coming from the left, they cannot enter this magnetic region of magnetic field, so they have to bypass the region. So what happens, the electron comes from the left hand side, they bypass the region, and the electrons are recorded by the detector or the screen which is placed here. Now, what we observe is a fringe pattern or regions of high intensity and low intensity on the screen. And what is important here and what is very surprising is that when the magnetic field inside this region is changed, the fringe pattern starts varying. And that is very surprising because if you think of it classically, this is the region, field-free region, so there is no magnetic field here. So what happens is that the electrons do not experience any magnetic force. And by the way, here we are talking only of magnetic field, there is no electric field or gravitational field, etc. This Aharonov Bohm effect can also be observed with electric field and gravitational field, but in this lecture we are not going to deal with those topics. Here we will be concerned only with magnetic field. So what happens is that when the magnetic field is changed, the flux in this region changes, and what is observed is that there is a periodicity in the fringe pattern. So if your fringe pattern, if the flux is changed by 2 pi h cross by q, then what we see is that the initial fringe pattern is restored. So the fringe pattern varies periodically with the magnetic flux with the periodicity 2 pi h cross by q. So what we are going to do in this lecture is try to understand why this thing happens. Even if there is no magnetic field in this region and this region, but just by changing the magnetic field in this region, you see a change in fringe pattern along the detector. So we'll go to the next slide. So this is the experimental setup. So in this experimental setup, we have an electron source here, and this is the screen. The screen actually prevents the electron from crossing into this region. This region contains the magnetic field. The magnetic field is produced by a solenoid. Okay, let me just erase this. So the magnetic field is created by a solenoid. So this is my solenoid. You can see by passing current through it you can produce magnetic field, and the electron comes, it cannot penetrate this region, so it has to bypass this region. And what happens, this is the detector, you get fringe pattern on this detector. And if you change the magnetic field in this solenoid, what we observe is a variation in the fringe pattern, and the same periodicity that we discussed in the last slide is observed. So the question is, what is it that's happening? So in order to understand that, we'll go to the next slide. Sorry, so I just erase this one. So what is the plan? Plan is, in order to understand Aharonov Bohm effect, we have to understand interference. What is interference? We have to understand electric fields and the corresponding electric and magnetic fields and the corresponding potentials. We have to understand what is Hamiltonian and Lagrangian. Then we have to understand what is path integral. And finally, we will understand what is the theory of Aharonov Bohm effect. So once we understand this interference and we understand fields and potentials, Hamiltonian, Lagrangian, path integral, we will be able to understand this effect. And what is the takeaway from this effect, that we are going to discuss at the end. So we start with interference. So we know what is interference. So interference is like here, two waves meet at a point with phases phi 1 and phi 2, and the resultant amplitude at that point is given by A1. Here it is given by A1 exponential I phi 1 plus A2 exponential I phi 2. Here I have written in as a complex number, because complex numbers are easier to handle. I could have written cos phi 1, cos phi 2, but instead of that I have written exponential I phi 1 and exponential I phi 2. So what is the picture? Picture is like this. So we have a screen. So there is some wave is coming. This the wave number 1 and this is the wave number 2. So this one, when it reaches here, it has a phase of phi 1. And this wave, the second one, when it reaches this point, has a phase of phi 2. So the net amplitude is AT, A1 exponential I phi 1 plus A2 exponential I. This is the amplitude here. So what is the intensity? Amplitude doesn't give us intensity. So to find the intensity, what we have to do, we have to multiply. AT is a complex number. So we have to multiply AT by its complex conjugate. Then we will get the intensity at this point. And we know what is the complex conjugate. So what is the complex conjugate of AT? It is AT bar. And AT bar is given by AT bar is given by A1. A1 is a real number, and e to the power minus I phi 1 plus A2 e to the power minus I phi 2. This is my 80 bar. So if I multiply 80 and 80 bar, it's not very difficult to see. We get this expression, a1 square plus a2 square plus twice a1 a2 into cos phi 1 minus phi 2. So this is the part which leads to variation of intensity as we go across the screen, this phi 1 minus phi 2, because as we go across the screen this phi 1 minus phi 2 varies, and that leads to interference pattern. So the fringe depends on cos phi 1 minus phi 2. So that's how we get maximum intensity and minimum intensity depending on phi 1 minus phi 2. If phi 1 minus phi 2 is 0 or some integral multiple of 2 pi, you get maximum. So that is the concept of interference, and this is what we are going to use later on. And let me erase this. In the next slide we are going to study electromagnetic fields and potentials. So we know that electromagnetic field means electric field and magnetic field. So electric field is E and magnetic field is P. And the electric and the magnetic fields are governed by Maxwell's equation. There are the four Maxwell's equation. So one of them is divergence of B is equal to 0. So this is one Maxwell's equation, right? So this is one Maxwell's equation, divergence of B is equal to 0. So another Maxwell's equation. So this Maxwell's equation immediately leads to what is called B is equal to curl of A. That is, this B is equal to curl of A automatically satisfies this Maxwell's equation, because divergence of curl is always 0. So this A is having a special name. So this is called the magnetic vector potential in electrodynamics. So this is important. So this is what we are going to deal with. So instead of B, we are going to deal with A. So this is one of the Maxwell's equation. This is another Maxwell's equation. That is curl of E is equal to minus del B del T. This equation can be recast in another form where we write E as minus of gradient of phi minus del E del T. Once we write this equation, this relation, if we substitute here, immediately satisfies the Maxwell's equation. So instead of this, we can use this. So here we have written in terms of a magnetic vector potential, and this phi is a scalar potential. So we have two potentials, scalar potential and a vector potential. And these potentials are not uniquely defined. It's not that for a particular B you have only one definite value of A, and for electric field you have only one particular value of phi. It's not like that. They can vary, and that is where the concept of gauge comes in. Means you can use different definitions for A and phi. So we will come to that later at the end. And there are two other Maxwell's equations involving divergence of E and divergence of E and curl of B. Those we are not writing here since we won't be dealing with them. Okay, so what is important here is that when the magnetic field is 0, the magnetic vector potential is not 0. So B is equal to 0 does not imply is equal to 0, and this is the fundamental thing. And because this is what will lead to Aharonov Bohm effect. We know what is a magnetic flux. Magnetic flux is, suppose we have an area like this, and you have magnetic lines of force coming out like this, right? So the magnetic flux across this area is given by integral of B dot ds, where this integration is across this entire surface. That gives us the magnetic flux across this region. Or B we know is curl of A, so we can write it as curl of A dot ds, and then we will use the theorem in vector calculus, which is the Stokes theorem. So curl of A dot ds immediately leads to A dot dr. So this A dot dr is along a closed loop. So this integral is over this surface, and this integral is a line integral. It is along this closed loop, this loop. This is by the virtue of Stokes theorem. So A dot dr is along this closed loop, right? So let's so why do we say that when B is 0, A is not 0? So that thing will be very clear here. So this is my surface. This is the surface. Okay, so this is the surface. This is the surface we are talking about, and this is the contour for the surface. This is the contour for the surface, right? So we are calculating the flux across this region. So when we calculate the flux across this region, so here there is no field. The field is only there in the portion that is shown here as black. So this one will have a flux. Okay, so your A dot dr will be along this loop. This is the contour for integration. So A dot dr is equal to the flux, and you know this. So we have magnetic field here, so the flux is non-zero, so your A has to be non-zero. Whatever the value of A is, it cannot be 0 everywhere. So that proves that if B is 0, so here B is 0 everywhere. This is a field free region, but A is not 0. B is non-zero only in this small portion. And we go to the next slide. Now the next topic. So what we have covered interference, and we have covered electromagnetic fields and potentials, that is vector potential and scalar potential. Now we are going to this concept of Hamiltonian and Lagrangian for charged particle. Hamiltonian and Lagrangian is a way of doing classical mechanics. We can do classical mechanics using Newton's laws, or we can use a more sophisticated approach, which is the Hamiltonian and the Lagrangian. For a charged particle in a magnetic field, the Hamiltonian is actually written as 1 by twice m p canonical minus q. Q is the charge for the particle, A is the magnetic vector potential in which the particle is moving, and whole square. We know that for a so this is canonical momentum. This canonical momentum is not equal to the regular momentum that we come across in Newtonian mechanics. So this is particularly interesting for charged particle in magnetic field. This canonical momentum and regular momentum are not the same. So the Hamiltonian is given by 1 by twice m p canonical minus qa whole square. So this Hamiltonian is a function of canonical momentum and the position x, which is reflected through A. For a free particle, the Hamiltonian is given by we know that it is given by p square. It is given by p square by twice m. This is the Hamiltonian for a free particle. In this case, the canonical momentum and the regular momentum are the same for a free particle. But in the case of a charged particle, it's not. So, we'll go to the next point. Next point, instead of the Hamiltonian function, we can use the Lagrangian function. The Lagrangian function gives you the same information, but its variables are different. Here, the L is a function of dx dt and x, unlike Hamiltonian, which is a function of canonical momentum and x. So, for a charged particle in magnetic field, the Lagrangian is given by half m dx dt whole square. So, this is the part that we know. This is the part that we know, which is the free particle part, and this is the part which is the magnetic potential, which is velocity dependent. So this part is velocity dependent. This is very characteristic of a particle moving in magnetic field. So this is velocity dependent. Velocity dependent. We'll be working with the Lagrangian. So this is velocity dependent. So we have the Hamiltonian for a free particle, a Hamiltonian for a particle in a charged particle in a magnetic field, and we have the Lagrangian for a charged particle in a magnetic field. And we also define something very important in Lagrangian and Hamilton in Lagrangian mechanics, which is called the action. So this action is L dt. So this L dt is evaluated along a very particular path, starting from some initial position and ending at a final position. So we know the coordinates at the initial position and the final position, and the path, and this L dt is calculated along a particular path. So this is a path dependent. If you choose a different path, then my action will come out to be a different quantity. So what is here is, so L is a function of the free part and the velocity dependent part. So the free part I have written as S0 IF. So this is calculated along a particular path starting from I and ending at F, and the second part is the potential part, which we can see easily that it can be written as an integral I to F A dot dx. Right? So it's L dt, so dx dt dot A times dt is nothing but A dot dx. And our next slide is path integral. So now we know what the Hamiltonian and the Lagrangian of a free particle is, and how to find out the action for how to find out the action for a particle. We know the Lagrangian and the Hamiltonian for a particle in a magnetic field, and we know how to find the action also for such a particle. Now we go to the concept of path integral. In the path integral, this concept is this path integral concept is another way of doing quantum mechanics, equivalent way, and this concept was put forward by Richard Feynman. The concept is something like this. So here you can see that we have the x-axis and we have the time axis, and so it's like this. Okay, so we start from here. So this is my initial position I, and I go to some position. So this is my I. Okay, so this is my initial position I, and then we have a final position here F. So this is the final position F. So from I to F, I can go in various ways. I can take this path, or I can take this path, or I can take this path. In fact, there are infinite number of paths which will take us from I to F. So this is my x-axis here, and this is my time axis. Correct? So what the path integral approach tells us, for every path there is a transition amplitude. So the particle is going from this point to this point along all the paths. It's not that it's taking this path or this path or this path. It's not like that. It's going from this point to this point along all the paths, and for each path there is a transition amplitude. So in that transition amplitude is given by exponential this one, exponential I by h cross L dt. So L dt is, so if I'm going along this path, so this is calculated along this path. If I'm considering this path, this transition amplitude is being calculated along this path. If I'm going along this path, then this transition amplitude is being calculated along this path. But the particle actually is going from this point to this point using all the paths. So this is path integral with for every path there is a transition amplitude. So the total transition amplitude from I to F is actually the sum of all the transition amplitudes. So the total transition amplitude from I to F is summation over all paths exponential I by h cross L dt. This is path integral. Or in a more sophisticated notation, if you write it in terms of integral, then we use what is called a capital D. Generally, in usual regular integral, we use a small d to denote integration, but here this is integration over all parts. So you use capital D, integration over all parts, and this L dt is actually the action that has been evaluated along a particular path. So I write I by h cross S IF. I is the initial point, F is the final point, xt, because this action depends on the path that has been chosen. So the total transition amplitude from I to F is this. Sum over all paths, or in a more sophisticated notation, dxt exponential I by h cross SIF xt. So we are seeing that we are just substituting the value of for a particle in magnetic field, we are just substituting the value of the action. Here the action is S0IF xt. This is the free particle action evaluated along that path, and this is the potential part that is being evaluated along the path, and this we have already deduced before this part. So we just substitute the value here, and now we have everything. So now we are ready to discuss the theory of Aharonov Bohm effect. So let's see what happens. So in Aharonov Bohm effect, what happens is, so the electron comes, okay, so there is a region which contains magnetic field, okay, this is the region that contains magnetic field, okay, and then there is a what you call a recorder or a screen. So this electron, So Aharonov Bohm effect is actually about a single electron. So this electron can, so suppose we are interested at this point, so this electron can say go like this, or this electron can go like this. Okay, so this is the region containing magnetic field. So this electron has to bypass this region because it cannot enter. So one part, so electron is a wave, so one part of the wave goes like this and the other part of the wave goes like this. This diagram is not very accurate, but I have drawn this to give you an idea about what is happening. So this part is the upper part, so this I denote by U, and this is the lower part. So there will be many paths that will take in the upper portion that will take you to that point, or in the lower portion there will be many paths that will take you to that point or take the electron to that point. So this is the idea. So the electron comes and then it's split. A part of the wave goes to the upper region and part of the wave goes to the lower region, and they recombine here. This is the upper portion, this is the lower portion. And now we are going to use path integral. So here, so for the upper region we have a path integral. So I am going from I to f. So the path integral to the upper region is dxut exponential I by h cross s0 to if xt. So this is evaluated along the path and a particular path, and then I to f q a dot dxu. Superscript denotes that we are in the upper region. This is a path in the upper region, and then we integrate over all the paths in the upper region. Similarly, there will be a transition amplitude A. So this is the transition amplitude for A upper. Similarly, we will have a transition amplitude for A lower, and that will be, here U will be replaced by L. So what we have is this. So we have this. U will be, so here it is U, here is L. So we are integrating over all the parts that are in the lower region, and then exponential I by h cross s0i. So this is evaluated along a particular path in the lower region, and this integral is calculated along that particular path, and then we sum over all the paths that are in the lower region, and that will give me the AL. So we have found out what is A upper, that is the amplitude, transition amplitude for all the paths in the upper region. So this is the transition amplitude for all the paths in the lower region. So the total transition amplitude is this. So the total amplitude, so this is the total transition amplitude. A transition is equal to AU plus A lower. So just like we have done in the case of interference, the intensity at F is A T multiplied by AT complex conjugate. So in complex conjugate, the i's become minus I. So if we do the calculation, we will have one of the terms like this. If we do the calculation, we will have one of the terms which look like this. One term will look like exponential plus I by h cross I to f, then q a dot dxu minus I to f a dot dx. Okay. So we will see. So we will see what this implies. So let's see. So let's erase this. Okay, and let's go here. So what we have is, so this is the region of magnetic field. So this is my screen. So this is one path and this is another path. Okay, so we calculate A dot, so A is a vector, dot D x, x is a vector, this is U superscript means upper. So we are calculating this along this path, and this integral sign is there. We are going from I to F. This is the upper and this is the lower. Similarly, there is another integral, that is minus I, and then we have F, then we have A dot D, and this is the superscript L. This is evaluated along lower path. So this actually means, what does it mean? It means I to F, the first part, sorry, so this means I to F, and then we have A dot dx u, and then plus, because of the minus sign we will have not I to F, now we will have, so this will be go as F to I, and A dot dxl. Okay, so this one is A I to F, so this is my I, this is my F. So A I to F, so A dot dxu along this path from I to F, and this one is A F to I, A dot dxl. So this is actually an integration along a closed loop. So this is actually integration along a closed loop, right? So this is integration along a closed loop. So A dot dx, and we know that A dot dx, this is, we just put the vector sign if you want, and this is actually this A dot dx, and this is actually can be written as B from Stokes theorem, B surface integral B dot ds. Right? Because from Stokes theorem, A dot dx becomes curl of A dot surface integral, and curl of A is B, so this is phi. That is how phi comes into picture. Okay, so this is how phi comes into picture. So you can erase it now. So here that's why we have written exponential plus minus I by h cross phi. So this term is actually phi. Phi is the flux through that region which contains the magnetic field. So if you do this, complete the calculation, what you get is this. You get the cost term. So simplifying, we will get cos q phi by h cross, and this you can see is a periodic term. That is, if phi, so what you can see here, this is a periodic term, and that is how we get the periodicity in the interference pattern. So if phi goes to phi plus 2 pi h cross by q, then we can see that this cost term repeats its value. That's why we say that this the interference pattern has a periodicity of 2 pi h cross by q, right? And the next one is, so the final slide is, so what is the takeaway? So what did we learn here? We learned something very important. So in classical electrodynamics, the electric and the magnetic fields are considered as fundamentals, and these A's and V's, that is the magnetic vector potential and the scalar potential, they are just considered as mathematical constructs. That is, they don't serve any fundamental value. But in quantum mechanics, what we see is that these gauge fields, this A and V, they are fundamentals. That is, even when B is 0, because of the presence of gauge fields, we have quantum mechanical effects, and one such effect is the Aharonov Bohm effect. So I want to end here, and thanks for bearing with me.